Allah, the god of oil, put all of that oil in the Persian Gulf, he had a very odd sense of humor. But that is the crux of the matter for the oil business. If you have a long period of time in which to adjust your weight, you can do so. For instance, the United States was, in 1979, was like a 190-pound man, and he has knocked his weight down to 150 pounds to 1983. And this is feasible. But if you only have 1 month to do it, and you don't have any oil, then you starve to death. And this is the difference. The Persian Gulf is a tinder keg, and it is not going to go away. It is where all of the oil is.
And if the supply of oil were to stop suddenly, then the whole of the Western world would grind to a halt, at least so far as transport is concerned. The Middle East has always been an area of tension. Religious and cultural differences between neighboring countries and the desire by outside nations to gain control of the oil has meant that the supply from here has always been at risk. But supplies have continued because oil is easily produced. It brings in a surplus of petrodollars, and the Middle East has some 60% of the world's reserves. Although it's now known where most of the world's other oil basins are, still the Middle East dominates the scene. In recent times, the industrialized world has been made painfully aware of the costs involved in maintaining a supply of energy for its industries. As a result, oil has become an even more precious physical resource. But it hasn't always been like that. The earliest discoveries of oil were those in Arabia, and there it was literally dug out of the ground. Hand-dug wells provided the early oil for lamps, but it was drilling that brought oil in quantity. In the early days, the oil often gushed to the surface under its own natural pressure. Oil was discovered throughout the world, but the first major industry was in the United States, where most people got in on the boom and tried to pump as much oil as possible. Nobody thought of oil as a non-renewable resource. These were the days of plenty, when many individuals had their own supply. Oil by the barrel was the order of the day, and billions of barrels were produced during the 20s and 30s. But as this boom continued, some experts had the foresight to realize that maybe oil wouldn't last forever. The first guesses as to how long oil would last were very varied. There was little geological understanding of the meager evidence, and so estimates of lifetimes fluctuated wildly. Only in 1956 was the first real science put into understanding production cycles from oil fields. Oil geologist King Hubbert was the first man to apply objectively based statistics to this problem.
This graph here is a theoretical graph of the rate of production of any exhaustible resource, such as oil or gas or coal. And we have the production rate plotted against time, and initially it starts at 0 and it goes up more and more steeply. Ultimately, it'll reach some climax as the resource begins to be scarce or difficult to discover, and then it goes into a long decline, not abruptly, but gradually back to 0. This technique I used in 1956. The date is interesting because at that time the curve was still going up very steeply, and the average opinion, informed opinion of the people of the U.S. Petroleum Industry was that this peak date would not occur before the end of this century. A common expression was it wouldn't happen in my lifetime, or my grandchildren could worry about oil. I don't have to.
Dr. Hubbert gave his predictions for American reserves using the oil industry's own data on the amounts of oil so far produced and that left in reservoirs below the ground. For this, the pessimists gave 150 billion barrels. The optimists gave 200 billion barrels. Hubbert showed that the difference between these figures has only a small effect on the date of peak production and on the lifetime of American oil.
So at that time, I predicted that the peak of crude oil production in the United States would occur within 10 to 15 years from the date 1956. It actually occurred in 14 years, namely in 1970.
At first, few people understood his predictions, so he broke them down into 3 curves, One for the amount of oil being taken out of the ground, the production curve. One for the amount of new oil being discovered, the discovery curve, which of course peaks a little earlier, and a third for the rate at which known reserves were changing. In the early years of the US industry, discoveries exceeded production, and the rate of change of reserves was positive. In other words, reserves were increasing. As time progressed and fewer discoveries were made, so they were outstripped by production, and the rate of change of reserves became negative. So known reserves were decreasing. Those were the predictions in 1956. What about the facts? The production curve matches almost exactly. Whilst the discovery curve is much more erratic, it still shows that the peak has been passed, and this means that known reserves are decreasing, so the rate of change of reserves is clearly negative. So the US oil industry has already passed the peak of its Hubbert life cycle. Whilst Hubbert's theoretical predictions were addressed to the US oil industry, the most mature land-based oil industry in the world, the lessons learnt can be applied elsewhere, for example to the rest of the world's onshore fields, and similar graphs can be drawn. The peak for world oil will come later, and political events will make the curves much more erratic. But when Hubbert produced his predictions, exploration had been almost purely land-based, and the oil-rich continental shelves remained virtually unexplored. One breakthrough in the mid-1960s allowed all these areas to be assessed: digital seismic.
The impact of digital seismic recording is that it completely changed the effectiveness of exploration for oil offshore all over the world. As a result of that and the technology that followed in the North Sea, it was possible to explore on any continental shelf in any part of the world, which was done.
Since the late 60s, when digital seismic came on stream, all of the continental shelves of the free world which are politically accessible have been explored, and the biggest fields have been drilled. Even with this new technology, there's still the same underlying trend. Digital seismic has given us a much more accurate feel for total reserves, and now we know that there are no new basins to be discovered. So crude oil supplies are finite and will run out in the 21st century. One way of extending the lifetime of oil is to get more oil from existing fields. Not long after the advent of the oil industry, the natural pressures in most reservoirs became insufficient to drive the oil to the surface, so pumping started. Not just pumping to extract oil, but also pumping water, gas and steam in to drive out more oil. Expensive liquids called surfactants, which lower surface tension, are also being used. The tighter or less permeable the reservoir, the more energy is required. But there's a problem with all these techniques. You have to put energy into the ground to extract the energy resource. So there's a decreased return on the energy budget. Such is the problem in most reservoirs that other methods of enhancing the recovery were tried with explosives. As the explosives got bigger, inevitably this involved nuclear explosions. And in the southwest states, there were several underground experiments with nuclear weapons designed to increase reservoir permeability. Such was the energy released that the mountains were shaken. Oil and gas did flow in greater quantity, but they were now contaminated. And such were the protests from environmental groups that production had to be stopped. However, there are other ways of getting oil from tight reservoirs, not least mining it. And these are the Athabasca oil sands, one of the world's largest deposits of oil of any type. Every hour, thousands of tons are extracted by ship-sized machines and sent off to the processing works. About 30% of this pile is bitumen, coating the sand grains. And the enormous works is designed not to refine oil, but merely to extract it. This is done in huge steam-filled tumbling drums. The oil sands reside in the drums for about 15 minutes, reaching temperatures of 200 degrees. And gradually, the bitumen loosens off the sands. Stones and sand come out at one end, and crude oil from the other. But the investment to get this crude oil is enormous. Plants like this cost billions, and the amount of processing energy involved is only marginally less than the energy value of the oil produced. But here it works because the price of oil has been high enough since 1974 for these huge reserves to be extracted economically. There are other substantial reserves of oil sands elsewhere in the world. The problem remains that the oil is expensive and few of these deposits are being exploited. But there's another potentially important source of oil which occurs in solid form. This is Colorado. These valleys and mesas are carved out of this rock. It's finely laminated on a sub-millimeter scale, and it consists of brown muddy bands interleaved with paler silty quartz bands. Now, late last century, workers building a railway through this wilderness used rocks like this to surround their fireplaces, and they found something quite unexpected. Rather than preventing the campfires from spreading, they'd actually found rocks that burned. So what those workers had discovered, unwittingly, was one of the world's major oil reserves, the oil shales of the western United States. In late Cretaceous, early Tertiary times, a vast inland lake covered the area which now represents Wyoming, Utah, and Colorado. And here, lake deposits laid down an 80-meter thick layer of oil shales, now preserved in two basins. They're capped by limestones, but the whole deposit consists of very fine layers. The thin layers are thought to represent annual variations in the depositional conditions. The dark layers, in fact, are very rich in organic debris, the remains of plant life which flourished in and around the lake during hot seasons. And the paler, silty layers represent sediment washed in from the surrounding land masses during rainy seasons. Now, the organic matter in this sediment probably makes up about 15% of the volume, and it's mainly in the form of long-chain sapropellic hydrocarbons of the type that we find in liquid crude oils. Now, how do we get a useful product out of this material? This is all that remains of the first attempt to mine oil back in 1919. But since then, research into extraction has continued here and in other places. In Parachute Creek in the 1960s, for the first time, modern equipment was used to mine oil shales underground and bring them to the surface for retorting. It takes about 1.5 tons of oil shale to produce a barrel of oil, so the scale of mining is vast. This is still only an experimental retort which worked for a few years back in the 1970s, but what they did find was that they could get oil. But this plant and other attempts have been hindered by two problems: a simple case of economics and complex environmental issues. The whole of this valley was required for waste dumping by just one of the smaller proposed mines. Thousands of acres would be needed if surface retorting ever becomes a reality. Barren land is common in Colorado, but water isn't. The planned processing plants required water supplies on a huge scale, and they're simply not available in this semi-desert. So other methods of producing the oil shales have been tried, and the first successful venture lies on the Colorado-Utah border, where Geokinetics Corporation are trying a novel method of in situ retorting. The oil shales here are close to the surface and are flat-lying. A series of boreholes is drilled in rows across a large tract of land, deeper at one end than the other. timed explosive charges break up the oil shale, leaving lumps with voids between them. Therefore, the reserves are now permeable. Air is pumped in at the shallow end and a fire front started. The fire moves through the shale, liberating oil in advance of its passage. This oil trickles down the sloping base of the retort and collects and is then pumped to the surface. That's the theory, but what does it look like in practice? This is one of two working retorts. These are the air pipes which force air in at one end of the retort, down into the expanded oil shale under considerable pressure. The fire front would have been lit some months ago and is working its way slowly across the retort area, meters below the ground. And at the other end, oil.
This shale oil that we're producing here today represents a number of firsts in the history of the state of Utah. Geokinetics is the first company ever to produce significant quantities of shale oil. We're the first company ever to sell that shale oil to a refinery and pay royalties to the state of Utah. And this oil is the first synthetic fuel produced, refined, and marketed within the state. At present, this is the only significant production of shale oil in the United States.
So the technique works, but at the moment it's not fully commercial. To improve the yield of oil, many more retorts will be needed. A variety of different environmental problems also needs to be solved, but at least the principle of in situ retorting has been proved. Using the geokinetics process, there's no problem with water shortage, because during the process, water is actually produced. Oil shale production on a commercial scale is being attempted only in the United States, but there are other reserves elsewhere in the world. For instance, back at the turn of the century, Britain had a thriving oil shale industry in the Midland Valley of Scotland, but cheaper supplies from conventional sources made these uneconomic, as has been the case with most attempts to win oil from shales or sands. So the oil shale deposits of Utah, Colorado and Wyoming could provide vast new supplies of liquid fuels. But first, much more work is needed on the large-scale variety of extractive technology. Now, another hydrocarbon resource which could provide the key to liquid fuel supplies is coal. And as you know, coal is much more abundant than either crude oil or natural gas. So to find out about the conversion of coal into other fuels, I visited the University of California at Berkeley, where experiments are being carried out using a purer form of carbon, graphite, which has reacted with steam to produce methane, the first step towards liquid automotive fuels. When added to the powdered graphite, various catalysts enhance favourable reactions at low temperatures. There is the potential for a breakthrough in economic terms, as the gasification process would then require less energy in commercial plants scaled up from these experiments. The tube containing graphite and catalyst are placed inside a furnace capable of heating the specimen up to 500 degrees centigrade. After drawing water in to produce steam, the reaction gets underway. The emerging gas is collected for analysis. This is known as the streaming or flow experiment. Graphite normally reacts with steam at high temperatures greater than 500 degrees centigrade to produce carbon monoxide and hydrogen. And what is being attempted here at this relatively low temperature is to find suitable catalysts so that graphite and steam will react to produce carbon dioxide and methane. Various combinations of catalysts are being tried, and by analysing the gases produced, their success is evaluated. So far, alkali metal catalysts are proving a key factor in the production of some methane at low temperatures. So the correct combinations of temperature and catalyst for the efficient production of methane from coal are being actively researched. To understand why a particular catalyst is more efficient than another, the experiments are repeated under more precise control. In this experiment, a polished graphite surface is specially prepared. The catalyst is impregnated on the surface. And here, a high vacuum chamber is used so that atmospheric contaminants can be removed before the experiment proceeds. This allows the gasification process to be more carefully controlled and the reaction surface to be studied after a contaminant-free reaction. Just as in the earlier streamflow experiment, the gases are analysed and yields compared so that the influence of surface chemistry on methane production can be evaluated. This fundamental work will complement the prototype streaming experiments, which hopefully mimic the industrial process for the low-temperature conversion of coal to methane gas. The ultimate attraction of research like this is that coal reserves far outweigh not only conventional crude oil reserves, but also the reserves in oil sands and shales. Moreover, coal is more evenly distributed around the globe. The likely future will see enormous open-strip coal mines feeding gasification plants, and the resulting gas used to make liquid fuels like methanol. But there's also a simpler and cheaper feedstock for methanol readily available: natural methane. World resources of natural gas are still huge, despite the unbelievably wasteful practice of flaring wet gas during oil production. Fortunately, this practice is gradually diminishing, and throughout the hydrocarbon-based industries, there's an increased drive to become more efficient. Now, in 1956, King Hubbard was very much a voice in the wilderness. But since then, his predictions for the future of resource modelling have not only been proved, but have also become common knowledge. His understanding of the finite nature of crude oil can be applied equally well to all other hydrocarbon resources. And of course, present recoverable reserves of crude oil, natural gas, oil shales, and even oil sands will all one day be exhausted. However, the problem is not merely one of resources, because the present recoverable reserves of oil hydrocarbons are quite adequate to last until nuclear fusion becomes a reality. So the real problem is not a shortage of resources, but is one of time and money for them to be developed. Now, of course, the days of cheap crude oil have gone, and such will be the price probably of conventional crude oil and certainly of synthetic crude oil that only the richest nations will be able to afford them. The cost and time required to develop a synthetic crude oil industry is quite considerable because massive mines have to be developed and industrial complexes on a large scale built. Environmental and economic and chemical problems all have to be overcome and the politics of such ventures negotiated. These problems all take time which even the Western world may not have.
If you have enough time to adjust, the world will work its way out of the problem if you have 20 years. But if you only have, as I said before, if you only have a month, that if the oil supply from the Persian Gulf is curtailed due to some political assassination or revolution event, then the economy of Japan and Western Europe may collapse within the month. It'll be very, very difficult to work its way out. You can starve to death in 1 month, but if you have a year or two, you can knock your weight down.